stand beneath a clear, dark sky, far from the glow of any city, and the cosmos presents itself as a vast dome studded with points of light, all of them seemingly fixed to the inside of a single enormous sphere, centered on you. This is the celestial sphere, an imaginary sphere of arbitrarily large radius onto which every star, planet, and galaxy is projected. It is a deliberate fiction. The stars lie at wildly different distances, Sirius about 8.5 light-years away, the red giant Betelgeuse roughly 550, but to the unaided eye those distances are invisible, and the sky behaves as though every object sits at the same immense remove. Because the projection keeps only direction and throws away distance, just two angles are enough to fix any point on it, exactly as latitude and longitude fix any point on the surface of the Earth. The celestial sphere is not a real object, then, but a coordinate convenience, and it remains, to this day, the natural stage for naked eye and positional astronomy. The sphere inherits its geometry from the Earth at its center. Extend the Earth's rotation axis outward, and it pierces the sphere at 2 points, the north and south celestial poles. The north celestial pole happens to lie less than a degree from a modestly bright star we call Polaris, the pole star. Project the Earth's equator outward, and it traces a great circle across the sky, the celestial equator dividing the heavens into a northern and a southern hemisphere, and the whole sphere appears to turn once a day about that polar axis, carrying the sun, the moon, the planets, and the stars from east to west. This is the diurnal motion, the daily wheeling of the sky, and it is, of course, an illusion, a reflection of the Earth itself spinning in the opposite direction, beneath a sky that is, over the course of a single night, effectively fixed. Because positions on the sphere are pure directions, the natural geometry of the sky is not that of a flat plane, but of the curved surface of a sphere. Here the straight lines are great circles, the largest circles that can be drawn on a sphere, each one cutting it into 2 equal halves, and distances are measured not in miles but in angles. The shortest path between 2 stars runs along the great circle that joins them, and their separation is simply the angle between them as seen from the center. It is worth stressing this point, because it is the deepest idea in the whole framework. Distance on the celestial sphere always means angular separation on the sky, never true separation in space. 2 stars that appear a finger's width apart may in reality be hundreds of light-years apart, one near, one far, for the sphere deliberately discards the third dimension, the dimension of depth. The celestial sphere model is very old. Greek astronomy, codified by Claudius Ptolemy in his great work The Almagest in the 2nd century, treated the heavens quite literally as a rotating crystalline sphere, carrying the fixed stars around a motionless Earth, with the sun, moon, and planets moving on additional mechanisms against that backdrop. The physical picture was wrong. There is no crystalline sphere, and it is the Earth that turns, not the sky. And yet the geometric machinery Ptolemy inherited was so accurate at predicting where things would appear that it survives, essentially intact in modern astronomy. When a planetarium projector paints the dome, or a star atlas maps the heavens, or a telescope's mount tracks a star across the night, each is working on the celestial sphere. The fiction, it turns out, is indispensable. 2 superimposed motions govern the changing appearance of the sky. The first is that daily rotation, the entire sphere turning once about the celestial poles, but it completes that circuit not in 24 hours, but in about 23 hours and 56 minutes. The sidereal day, the true time for the Earth to spin once relative to the distant stars. The familiar solar day is some 4 minutes longer, because while the Earth spins it is also creeping along its orbit around the Sun, roughly 1 degree each day, and so it must turn a little extra to bring the Sun back to the same place in the sky. Over a full year those 4-minute differences accumulate into one entire extra rotation. This is why the stars rise about 4 minutes earlier each night, and why the constellations on view at a given hour slowly cycle through the seasons. The second motion is annual. As the Earth journeys around the Sun appears to drift slowly eastward against the background stars, completing 1 full circuit of the sky in a year. The Sun's apparent yearly path is itself a great circle, called the ecliptic, the projection onto the sphere of the plane of the Earth's orbit. Because the Earth's spin axis is tilted, the ecliptic is inclined to the celestial equator by an angle of about 23.5 degrees, known as the obliquity. The 2 great circles cross at 2 points. The equinoxes, the point where the Sun crosses the equator moving northward around the 20th of March, is the vernal equinox, historically called the first point of Aries, and it is the single most important reference direction in all of positional astronomy, the zero from which the sky is measured. The sun's farthest swings north and south mark the solstices, equinoxes and solstices together define the seasons, and the band of sky through which the sun, moon and planets forever appear to move, because their orbits all lie close to the ecliptic, is the zodiac. Now, how do we actually say where something is? The most intuitive way is to describe its direction relative to your own horizon. This is the horizontal system. The point directly overhead is the zenith. The point directly beneath your feet on the far side of the sphere is the nadir, and the great circle exactly midway between them, 90 degrees from the zenith in every direction, is the horizon. An object's altitude is simply its height above the horizon, from 0 at the horizon to 90 degrees straight up. Its azimuth is its direction around the horizon, north, east, south, west, measured as a bearing. A star reaches its highest point and is said to culminate at the moment it crosses the meridian, the line running from due north over the zenith to due south. The great virtue of this system is its immediacy. It is exactly what a person or a surveyor's instrument measures directly. Its great weakness is that the coordinates of a fixed star are not fixed at all. As the sky turns, a star's altitude and azimuth change continuously through the night and differ for every observer at every location. Wonderful for telling someone where to look right now, useless for cataloguing the permanent positions of the stars. For that, astronomers need a frame that turns with the sky, and that is the equatorial system, the dominant framework for cataloguing the heavens. It simply projects the Earth's own grid of latitude and longitude outward onto the celestial sphere. The latitude-like coordinate is declination, the angular distance of an object north or south of the celestial equator, from the equator out to the poles. The longitude-like coordinate is right ascension, measured eastward around the equator, starting from that all-important vernal equinox, and right ascension is expressed, curiously, not in degrees but in hours, minutes and seconds, because the sky turns through a full circle in 24 hours, so 1 hour of right ascension is just 15 degrees of sky. The beauty of this system is that, because it is anchored to the Earth's spin axis, and to a fixed direction among the stars, a star's equatorial coordinates stay very nearly constant as the whole sky wheels overhead, precisely the permanence the horizontal system lacked. The two systems are joined by a single elegant fact: the altitude of the celestial pole above your horizon is equal to your own latitude on Earth. Stand at the North Pole, and Polaris hangs almost directly overhead. Stand on the equator, and it sits right on the horizon. This one relationship is the workhorse of telescope pointing. An equatorial telescope mount aligns one of its axes with the celestial pole, so that, to follow a star, it need only turn that single axis smoothly at the rate of the sky's rotation, cancelling the Earth's spin and holding the target locked in view. But there is a subtlety. Because the vernal equinox itself is slowly moving, a set of equatorial coordinates is only meaningful with respect to a stated moment in time, a reference epoch. Nearly every catalogue today uses the epoch known as J2000. Two further coordinate systems each make a particular class of problem simple. The ecliptic system uses the plane of the Earth's orbit as its reference, and it is the natural frame for the solar system, because the planets, the moon, the asteroids and most comets all orbit close to the ecliptic plane, so in these coordinates they scarcely stray from the central line, and their motion is easy to follow. It is the map you would draw to chart a planet's wandering. The galactic system, by contrast, is aligned not with the Earth or the Sun, but with the great pinwheel of the Milky Way itself, its latitude measured from the plane of the galaxy, its longitude running along that plane from the direction of the galactic center. It is the frame of choice for studying the galaxy's disk, its spiral arms and its populations of stars. And at the very heart of that coordinate system, almost exactly at galactic longitude 0, sits the true dynamical center of the Milky Way, a compact radio source called Sagittarius A star, which we now know to be a supermassive black hole, some 4 million times the mass of the Sun. Because the equatorial and ecliptic frames are both tied to that slowly drifting equinox, any position measured in them is meaningful only with respect to a stated epoch, and the modern standard is J2000. 0, defined as the instant of noon on the 1st of January, in the year 2000. For the most demanding work, the realized frame is the International Celestial Reference System, fixed not to stars at all but to the axes defined by distant quasars. objects so unimaginably remote that they are, for all practical purposes, perfectly motionless. This matters more than it might seem. Confuse a position given for the epoch 1950 with one given for 2000, and you introduce an error of roughly half a degree, the width of the full moon. An epoch is not optional decoration, it is an essential part of a coordinate. But why should the grid drift at all? The answer is precession. The Earth is not a perfect sphere, it bulges slightly at the equator, wider around its waist than pole to pole. The combined gravity of the moon and the sun pulls on that bulge, trying to tug it into line with the ecliptic, and this exerts a steady torque on the spinning Earth. Now, a spinning body does not respond to a torque by toppling over. It responds by precessing, its axis slowly sweeping out a great cone in space, like the wobble of a spinning top as it winds down. And so the Earth's axis keeps its tilt of about 23.5 degrees, but slowly changes the direction it points, tracing one full circle of that cone in roughly 25,800 years. The axis drifts about 1 degree every 72 years, slow by human reckoning, immense over the span of civilizations. The consequences unfold over the ages. Because the axis wanders, the identity of the pole star changes. Polaris marks the north for us now, but around 5,000 years ago, in the age of the pyramids, that role belonged to a star called Thuban in the constellation Draco, and in some 12,000 years' time it will pass to the brilliant Vega. Because the equinoxes are the crossing points of a moving equator with the ecliptic, they too slide slowly westward, dragging the entire coordinate grid with them, which is why the first point of Aries, named by the Greeks, has since crept backward and now actually lies in the neighbouring constellation of Pisces. This grand drift was discovered around 130 years before our era by the Greek astronomer Hipparchus, who compared his own careful measurements of the stars with records centuries older, and detected a shift of about 1 degree per century, a breathtaking feat of precision, achieved entirely with the naked eye. Superimposed on this smooth precession is a smaller nodding of the axis, called nutation, driven by the wobble of the moon's own orbit over a cycle of about 19 years. The constellations are humanity's oldest map of the sky, patterns imagined among the stars to make the overwhelming dome memorable and useful. They are not real groupings. The stars of a constellation usually lie at utterly different distances, physically unrelated to one another. They are chance alignments projected onto the sphere, and then given names and stories. The Western tradition descends from Mesopotamia and Greece. Ptolemy's Almagest catalogued 48 constellations, and almost every one of them survives on our charts today. But Ptolemy could map only the sky visible from the Mediterranean. The far southern heavens, never rising above the Greek horizon, remained blank to Europeans until their ships finally carried them into southern latitudes. The gap was filled during the Age of Exploration. In an atlas of 1603, the German astronomer Johann Bayer added a dozen new southern constellations, drawn from the reports of Dutch navigators, among them Gruz the crane, Pavo the peacock, and Tucana the toucan, exotic creatures for an age of discovery. A century and a half later, the Frenchman Nicolas Louis de Lacaille, observing from the Cape of Good Hope, introduced 14 more, and named them tellingly for the instruments of science and the arts: telescopium the telescope, microscopium the microscope, octans the octant, antler the air pump. One of his creations, Mensa, honours Table Mountain, beneath which he had worked, the only constellation in the sky named for a feature of the Earth. By the early 20th century, this inherited patchwork of overlapping, inconsistently drawn figures had become a genuine problem for a science that was growing ever more precise. The International Astronomical Union resolved it, fixing the canonical list at 88 constellations, covering the entire sky with no gaps and no overlaps. Precise boundaries were drawn, along lines of constant right ascension and declination, so that since then every constellation has been a rigorously defined region of the heavens, and every star, every galaxy, every passing comet belongs unambiguously to exactly one of them. They are wildly unequal in size. The largest, Hydra the water snake, sprawls across more than 1,000 square degrees, while the smallest, Crux the Southern Cross, occupies barely 68. And here is a curiosity: although the zodiac of tradition names 12 constellations along the sun's path, there are in fact 13 that the ecliptic crosses. The sun also spends time each year passing through Ophiuchus, the serpent bearer, a constellation the old astrological zodiac quietly leaves out. Everything we have discussed becomes concrete the moment you simply look up, and what you can see is governed first by brightness, the scale astronomers still use was inherited directly from the human eye. Hipparchus ranked the stars into 6 magnitudes. The brightest were of the 1st magnitude, the faintest the eye could catch of the 6th. In 1856, Norman Pogson made the scale exact, defining a difference of 5 magnitudes as a brightness ratio of exactly 100, so that a single step up the scale means a star about 2.5 times brighter. The scale runs backward, which forever trips up the newcomer. Brighter objects have smaller numbers, and the very brightest have negative ones. Sirius, the brightest star in the night sky, shines at magnitude -1.5, the full moon at about -13, the sun at about -27. The faintest stars a keen eye can reach, under ideal skies, hover around magnitude 6. Under a truly dark sky, perhaps 5,000 stars are visible over a whole night, yet from the heart of a bright city, light pollution can cut the limit to magnitude 3 or 4, leaving only a few hundred stars, and erasing the soft band of the Milky Way entirely. The atmosphere itself reshapes what reaches the eye. Air bends incoming light downward, refraction, lifting the apparent position of every object slightly higher than its true place. At the horizon, this displacement grows to about 34 arcminutes, which is actually larger than the diameter of the sun itself. The startling consequence is that at the very moment the setting sun appears to touch the horizon, its entire disk is already geometrically below it. We are seeing it bent from around the curve of the world. The same thick blanket of air near the horizon dims and reddens starlight extinction, which is why stars hanging low look faint and orange, their light strained through a longer column of atmosphere. And turbulence in the air makes the stars twinkle. The planets, showing a small disk rather than a true pinpoint, twinkle far less, which is one of the oldest ways to tell a planet from a star. The star flickers, the planet shines steady. Finally, geometry alone decides what you can ever see. Recall that the celestial pole stands at an altitude equal to your latitude. It follows that stars within that same angle of the pole never set at all. They wheel in complete circles through the night, and we call them circumpolar. Stars within that angle of the opposite pole never rise and are forever hidden from you. From the equator, no star is circumpolar, and over a year the entire sphere parades past. From the poles, half the sky is permanently up and half permanently unseen, the stars circling flat, parallel to the horizon. This single fact, pole altitude equals latitude, is why, for centuries, navigators found their latitude at sea simply by measuring the height of Polaris above the horizon. And it is why the constellations you grew up with depend so deeply on where on Earth you were born. There is one more subtlety to a real night. The transition from day to darkness is not abrupt, because the atmosphere keeps scattering sunlight after the sun has set. This is twilight. Astronomers mark 3 stages by how far the sun has sunk below the horizon. In civil twilight, the brightest stars and planets begin to emerge. In nautical twilight, the sea horizon is still faintly visible, the historic window for sailors taking star sightings. In astronomical twilight, only the faintest trace of glow remains. And only when the sun is more than 18 degrees below the horizon does the sky reach true astronomical darkness, deep enough to reveal the faintest naked-eye stars and the full sweep of the Milky Way. At high latitudes in summer the sun never sinks that far, and darkness never fully comes, the famous white nights. And at the poles, twilight and darkness each stretch on for weeks. The sun's own timekeeping, meanwhile, is subtly irregular. A sundial, which reads time straight from the sun, disagrees with a steady clock by an amount that drifts through the year, as much as a quarter of an hour either way. This is the equation of time, and it has 2 causes. The Earth's orbit is slightly off-circular, so the Earth moves faster in January than in July, and the sun runs along the tilted ecliptic, while our clocks track the equator. Photograph the sun at the very same clock time every day for a year, and it traces a slender figure 8 in the sky, called the analemma. And then there are the objects that refuse to keep their places at all. Our very word planet comes from the Greek for wanderer. For the naked eye, planets drift among the fixed stars from night to night, always near the ecliptic. Stranger still, an outer planet will now and then seem to halt, reverse and loop backward, retrograde motion before moving on. It is a pure illusion, caused by the faster Earth overtaking the slower planet on the inside track. To reproduce it, Ptolemy's Earth-centered cosmos needed a bewildering scaffolding of wheels upon wheels. The sun-centered model of Copernicus explained the whole loop, effortlessly at a stroke. The moon, swiftest of the wanderers, races once around the zodiac in about 27 days. and its monthly circuit, set against the sun's yearly march, drives the cycle of phases, and the occasional spectacular alignments we call eclipses. This entire framework, a sphere, a handful of coordinate grids, a slowly wobbling axis, was built over 2,000 years from nothing but the naked eye. And yet it underpins the most precise measurements in all of modern science. The leap in accuracy is staggering. The unaided eye can pin a star's position to about an arcminute. Tycho Brahe, observing without any telescope in the late 16th century, pushed that limit as far as it could go, and thereby handed Kepler the exquisite data from which he deduced that the planets move in ellipses. The telescope, the photographic plate, and the electronic detector each improved matters, but the decisive advances came from space. The European Space Agency's Hipparcos satellite mapped the positions of some 118,000 stars to milliarcsecond precision, finally fixing the distance scale of our stellar neighborhood. Its successor, the Gaia mission, transformed the field again, charting roughly 1.8 billion stars, with a precision reaching the microarcsecond, an angle so fine it is like resolving a single coin lying on the surface of the moon from here on Earth. At such accuracy, the comfortable picture of fixed stars dissolves into two motions the eye can never perceive. The first is proper motion, the slow, genuine drift of a star across the sky as it travels through space relative to the sun. Even the swiftest known, Barnard's star, takes about 180 years to cross a distance equal to the width of the full moon. The second is parallax, the tiny yearly ellipse a nearby star seems to trace, as the Earth swings from one side of its orbit to the other and views the star from slightly different angles. Parallax is the direct, geometric ruler of cosmic distance, yet even for the nearest star beyond the Sun, Proxima Centauri, the angle is less than a single arcsecond, which is exactly why the distances to the stars eluded measurement until the 19th century, and why mapping them at large demanded telescopes flown above the atmosphere. Because every star in the end is moving, the ultimate reference frame cannot be built from stars at all. It is anchored instead to the distant quasars, the blazing cores of remote galaxies, so far away that their motion across the sky is utterly imperceptible. Fixed to those beacons, the celestial reference frame is now defined to better than 1/10 of a milliarcsecond, and it is worth being clear about what all this settles. The geometry of the celestial sphere, the coordinate systems, the tilt of the axis, the rate of precession, the catalogue of 88 constellations. These are established, high-precision results with no scientific controversy attached to them at all. The great open questions of astronomy lie elsewhere, in the nature of dark matter and dark energy, in how fast the universe is expanding, in the physics of its first moments, and we will take them up in the chapters to come. But those harder questions can only be posed on a secure foundation. Before we can argue about how fast the universe expands, we must first agree to the microarcsecond, on where everything is. That agreement is precisely what the celestial sphere and its coordinates provide, the quiet, indispensable achievement that began, long ago, with shepherds naming patterns among the stars.